Good morning, all. Good morning and good evening, good afternoon to all who have joined the webinar today. Welcome to IEEE Future Tech Forum. This is the first of our series on artificial intelligence. And our first webinar is organized and facilitated in collaboration with Microsoft and my colleagues at Microsoft and with the AI Coalition, which my name is Chris Miacci, and I'm a chair of the AI Coalition as well. And I also work for Microsoft. And the presenters today are my colleagues at Microsoft. So the title of today's talk is an introduction to supporting AI workloads in the cloud, hardware infrastructure and other complexities in the cloud environment. So building and managing hardware infrastructure in the cloud plays a critical role in the development of AI training models. It provides essential resources needed to handle the complexity, scale, and computational demands of these workloads. In this session, we'll provide an overview of the hardware infrastructure that powers AI training models and the challenges that arise in the cloud environment. The discussion will begin from building the infrastructure to generating the model, and finally to the creation of the business value. And I want to present my two panelists today. First, I'm Chris Miacci. I am a senior software development manager at Microsoft, and I work in cloud and AI in the healthcare area. And my two panelists are Emma Montalvo. She is a senior technical program manager at Microsoft AI. And Sam Prakash Berry is a principal program manager at Microsoft Azure. And their full bios are in the registration for the webinar. So without further ado, I'm going to pass the presentation over to Sam and Emma.
Thanks, Christine. And so let's get started, right? I think Christine gave us a very, nice introduction of what we are going to touch today. To start off with, I think let's go to the agenda section. To set the stage for today's discussion, we are going to divide the presentation in two key parts. That is the background and AI in the cloud. And in the background, we are going to define what is artificial intelligence and explore what are the different type of AIs are there in the business, right? And what workloads involved in it. And also we'll take a closer look at what is generative AI, right? Which has seen an explosive growth with models like ChatGPT, Gemini, Copilot. Also, we are going to briefly explain how these models work, from large scale training to generating, I think, various content like text, images, and audios and videos. And lastly, we are also going to examine why cloud computing is so essential for AI, right? Covering how elasticity, scalability, and high performance computing in cloud is going to enable this rapid AI innovation. In the second section, we are going to dive into the infrastructure behind the AI, that what hardware infrastructure is required by these AI workloads, and also what transformations these cloud service providers are doing to enable these AI workloads run in their infrastructure. And later point of time, once the workloads are running on these machines, what challenges these companies see, and what are they investing, how are they pursuing to overcome these challenges. Okay, so let's quickly deep dive, right? So what is AI? High level, we are going to touch AI, as the name refers, is artificial intelligence. It replicates or simulates the human intelligence in the machines that can learn, reason, and adapt, right, to perform tasks that were traditionally required human intelligence. And we broadly define AIs into five categories. The first one is machine learning. It is a subset of AI that enables computers to learn from data and improve the performance, right? And without enabling explicit programming. And instead of we trying to write pre-written rules, ML algorithms usually try to identify patterns from large amount of data they analyze, they make predictions, and then they enhance decision making. And also it includes tasks like classifications, regressions, recommendation systems, and many more, right? And if you see today, the ML has become a backbone for many applications, which includes in financial services like fraud detection, predictive maintenance, or in the chatbot like customer behavior analysis. The next, I think, the AI type is the NLP, which is the natural language processing, which enables the computers to understand, interpret, and generate human language, right? Whether it could be spoken, unwritten. And NLP typically bridges the gap between the complex human communications and the machine. And this allows understanding and interaction that feel more natural, intuitive. And if you see today, we use a lot of chatbots, right? Over the business are using it. We are using AI assistants home like Google Home or Alexa. All these are incorporating NLP in their, I think, implementations. And that's where I think it has become very crucial to bridge that gap between human intelligence versus machine intelligence. The third one comes the computer vision, and this enables computer to interpret, analyze, and understand the way we visualize the data. Right, either it could be images or videos, and also it enables the machines to see how can they identify patterns, right, identified objects, and interpret visual scenes similarly to how we do through our eyes as human vision can interpret those. And it's widely used in the surveillance and quality inspections, and also in medical field like medical imaging. Next comes the deep learning, right? As the name suggests, deep actually it's a multi-layered neural network implementation that uses uh, deep understand try to analyze deep complex patterns in large amount of data, right? The way our human brain, I think, is structured, which deep I think deeper and complex, I think, nervous system, it's very similar to that. And so deep learning networks are particularly effective in processing the unstructured data like complex images, audios, and texts. And deep learning has been also used for facial recognitions, autonomous driving, and speech to text translations. And the last is the Gen AI, right? This is where we are seeing a lot of, I think, buzz in last couple of years, and which focuses on creating new content that resembles the existing data, right? Instead of just analyzing or predicting based on the existing information, which all the above models did very well, but the Gen AI takes it one step ahead, right? It takes the input and then gives us output in forms of text, image, or even generating a code or audio. And the standard classic examples what we see today are the chat GPTs or the co-pilots in the Microsoft, which work very well in the form of AI model. Let's go to the next slide. Okay. Now that we know what the AI is, let's talk about the evolution of AI, right? So at least we know by today, in today's world, we know that AI is not a new concept. And it was a bit surprising for me when I was starting research on the slide. I realized that AI went back up to several decades ago, right? It was almost in 1950s the roots was AI was rooted to. And the term AI was coined in 1956 at the Dartmouth conference by two researchers. And the early focus of AI was as mainly, I think, building machines that incorporated rules and logic to simulate reasoning. I think it was pretty fascinating for me to learn that it was almost 60 to 70 years ago this all AI evolution started. And starting from the 60s to 80s, the progress stalled actually, right? Because of limitation of computational power, unmet expectations, and also lack of, I think, good resources. The AI could make a huge progress. And that was famously called as the AI winters. And slowly after that, we saw a resurgence happening in the world of AI with improved algorithms and more in improved hardware, computational capabilities. It really reignited the interest in AI. And that's when I think we saw a lot of AI getting involved in medical diagnosis, finance, and the manufacturing industry. And that's when in late 1990s and early 2000s the machine learning era came in, right? With more data, with the dot-com boom, more data being available, and more, I think, evolved hardware, the machine learning simply took off. A lot of new algorithms came into picture during that era, like the decision trees, support vector machines, and regressions became mainstream. And we saw that AI shifted from hard code static rules to data driven learning, and that eventually translated into the rise of deep learning, right? And by 2010 we saw the deep learning came into picture, and also some introduction of GPUs also came at that point of time. The neural networks also, I think, became very popular during that time, which contributed to the image recognition, understanding complex networks, speech and language processing, etc. And that's when we saw companies like AWS introducing Alexa in 2010s onwards, which really was based on this NLP. And in the recent times, in the recent age, Gen AI has taken, I think, the lead here, which is combine all these learnings from all those years to build the next generation of evolution that we are seeing in form of the generative AI. So now that we know that the AI has been there from almost like a couple of decades, uh, so we can agree that AI is no longer a niche technology. So it has been in existence since 1950, and also I can say that it has become a core enabler across every industry, starting from you see automation, optimization, even personalization and decision intelligence. AI is creating a massive economic and social impact globally. Even countries like America, US, in countries like US, Europe, and Asia also competing to lead in the AI research, development, and innovation, right? And especially, and I was reading an article where China and India are also investing heavily in AI to foster the economic growth and the technological advancement. So a lot of industries, I won't say a lot, but every industry in the market is trying to be a player in AI, right? Take an example in the e-commerce, the retailers are trying to leverage AI to build dynamic pricing, inventory forecasting, and personalized recommendations, and also include customer sentiment analysis. Healthcare is also, I think, doing a great job. They are trying to use AI to diagnose diseases and to more accurately use, I think, AI models for computer vision and predictive analytics on uncertain fields of cancer research. So financial services have been using AI for a long time for fraud detection and risk modeling and algorithmic trading, and they are also now trying to enhance and further incorporate AI into their DNA for enhanced compliance and personalized financial products. And manufacturing has been using AI for chain optimization, predictive maintenance, and quality control as well. Now that we know companies have been adopting AI, let's try to understand what actually how these AI models work, right? What is the AI life cycle? And which I think MI is going to talk us through that section.
Thanks, Sam. Before we dive into generative AI specifically for this conversation, let's review the general process of building an AI training model to get a complete picture of what's involved. So first, the data must be prepared. Good data in is good data out. This may consist of managing outliers, normalization, labeling, feature engineering, dealing with missing values, things like that, to ensure the model can learn and derive accurate insights. For example, let's say we have the following features in a data set for housing sales. We have the price, square footage, and number of bedrooms. New features that we could add include price per square foot, labeling the home small, medium, large based on square footage, and cleaning up missing values for the number of bedrooms by using the median. At this step, the data can also be split into the training, validation, and test sets. This first step is very important to develop a good model. Second and third are the model building, training, and tuning steps. At these steps, multiple models are built and compared against one another to select the best one. Before any of these models start learning, the hyperparameters must be set to maximize the model's performance, and there are many different strategies to tune them along the way. After the models run, they are compared across several metrics like precision, recall, accuracy, and F1 scores, just to name a few. Once we do select that model, it's then deployed and used in production. At this point, the model can be integrated into an application or system to generate new content, make predictions, etc. Some of the examples of when these models are applied in the inference layer show up in the form of Copilot, ChatGPT, or Claude, for example. Finally, the model is monitored to check on what issues could arise. These issues could follow themes like 1, latency, maybe the voice assistant is experiencing delays and creating a bad user experience. 2, it's throughput. There could potentially be issues with the fact that the video streaming service that is now being launched is cutting out and there's data loss. Or 3, there's maybe drift. As Sam was mentioning, there are companies putting forth recommendation systems to users, but what happens when those user preferences change over time? Learnings from these types of issues can mean better tuning or even retraining the model. So now that we know how the models are generally built, we can start thinking about the requirements for running these training workloads and discuss how generative AI works specifically. So let's first define what generative AI is. Generative AI can create content in various mediums as seen in the graphic, and we'll dive into some of those use cases on the next slide. To create this content, generative AI requires a massive amount of data, sometimes in the order of petabytes, to establish patterns. This will come up again when we summarize AI training workload requirements. So peeling the onion back a bit further, we can see that there are many different types of generative AI models for various use cases. These use cases then map to specific AI training models. For example, you might have chatbots like ChatGPT, Copilot, leveraging that transformer-based model on the first line. You also see that there's image generation that can leverage generative adversarial networks or diffusion models depending on the exact scenario. Variational autoencoders can also help with image generation through image-to-image translation via face morphing or the changing of expressions in a picture. There is some overlap across these use cases, and hence why it is important to train your data with different types of models and measure the model's performance to then optimize your use case. To connect the underlying computational requirements of generative AI training models with the need for cloud infrastructure, we will specifically examine the high-level architecture of the transformer-based model, just to take an example. So with this slide, we will get under the hood of what the transformer-based models are doing to understand the computational complexities and why such immense computing power is needed. On the screen, you see that this model is leveraging a neural network made up of the input, hidden, and output layers. They can be further broken down into what you see as neurons. At the input layer, data is passed in. At the hidden layer, which could actually be multiple layers, data is then transformed. And then finally, at the output layer, there is a resulting prediction or classification that's made. Each connection between the neurons, you can see the equation in between each of those connections, has a weight for the importance of that input, plus the bias to form a computation that helps determine how the model should process language. In training, the model predicts, then calculates errors, and then updates the weights to minimize the errors and runs through it again. With the increasing complexity of these models, more and more of these parameters or calculations are made over time. The panel on the right shows the number of parameters calculated from 2018 through the GPT model in 2023, which reached about 1.4 trillion parameters calculated. It's important to note that all these computations need to be running concurrently as they are constantly adjusting to optimize the model. This is where significant computing power is required. I will now hand it off to Sam, who will help us summarize these requirements and share how cloud infrastructure supports these needs. Over to you, Sam.
Thanks, Emma. Can you hear me?
Yes.
Yeah, okay, thank you. So now that Emma has talked about how complex these AI models are, right? Specifically generative AI models and how much amount of data they process, how much complexity it involves. So let's try to understand is uh, what infrastructure requirements are required for running this AI workloads, right? So what does that mean that for the cloud service providers, what additional infrastructure they need to build to support these AI workloads, right? And at the same time, as we talked about, once these AI workloads are being hosted, what challenges they're incurring and what potential solutions are they pursuing today. So with this, we are going to push forward into the next slide, which we are going to talk about the need for robust AI infrastructure. And if we see today, the AI workloads, as we talked about, is computationally highly intensive, very, very data hungry, and also often unpredictable, right? Because as they scale up the model traffic. Hence, supporting them at scale requires an advanced infrastructure. And also, that is not only powerful, but also flexible, scalable, and reliable, right? So, AI finds it very, the AI players or the AI customers find it very, very expensive and cumbersome to build a standalone in house infrastructure because it not only needs hardware but also it needs software stack to get built. Also they need the people and resources to run these and maintain these in-house, right? And it comes with a cost. So that's where, as Emma was highlighting, these training models, which are these modern AI models, requires large amount of data, right, which can run into the petabytes, which can take even days, months, or weeks for running, which requires a massive parallel processing power, right? Like untraditional AI workloads, which can be able to run on a normal servers, compute-based servers. But if you look for these AI models, they require a specialized hardware, which are famously the GPUs and the TPUs of the world today, or the custom AI accelerators, right, which has the capability to process large amount of data. And this is one of the key requirements for the AI workloads, right? To have a high computational hardware. Then comes the scalability, right? Because scalability, elasticity is very, very vital for the AI models, right? There are periods when these models go idle or slow, as I was talking about in the inference phase. But when it comes to the training phase, which is very, very high demand, And these training models require a very high processing capability and vertical and horizontal scaling. And that's where the cloud infra comes plays a key role because of the existing infrastructure they have. And also, as we're dealing with a huge amount of data, the storage and network capability also plays a key role, right? They need high throughput and low latency, not only to process and train the data, but also able to transfer the data from one machine to other, right? And that's where these large data sets that gets generated, like the images, audios, videos, or the data it gets trained on, needs to be placed in the storage servers, right? And building that data storage capability is very critical. And next comes the deployment, right? So these, if you see, the AI models are very complex in nature, right? They need advanced APIs to get deployed. They need a secure or containerized environments to be run on. And that's where I think having that infrastructure in-house is very complex, and maintaining them is even more challenging, right? And that's where the cloud AIs already have these APIs built for the general traffic that are running today. And the last but not the least, the most important thing for these businesses are to have a cost optimized way to run this traffic, right? They don't want to invest a lot in AI to just to build the infrastructure and maintain them, right? And that's where the cloud service providers come with pay as you go model, right? Amount of traffic you run, amount of, I think, resources you are utilizing, then you will be metered accordingly. So that's a big benefit for these cloud players who are for these AI players who are trying to look for run their I think traffic in cloud world. So now that we have covered the needs of a robust AI infrastructure, let's quickly deep dive into what specialized hardware infrastructure is required for running this AI workloads, right? How these cloud service providers are trying to make themselves equipped for or enable themselves to run these AI workloads, right? If you see historically, right, the cloud service providers like the Azures of the world, or the AWS or the GCPs, they had a very robust cloud infrastructure which is capable of running complex non-AI related workloads, right? They had good network infrastructure, they had storage infrastructure, compute infrastructures, as well as robust data centers, right, hosting these servers as well. But what was missing was the new set of servers, right? New set of hardwares that are capable of running these AI workloads. So it was not a easy transformation, but not at all difficult one as well. They had their share of challenges to get this heavy lift done, but they started investing heavily on building this capability for the AI players to support these modern AI workloads right today, which involves, I think, large scale modeling and training. The cloud service providers invested heavily on these high performance computing servers, which is famously called as the HPC servers, right? And these are extremely high end servers which has the capability of combining these GPUs, CPUs, and high bandwidth memory and storage, right, with faster interconnects. And these, I think, servers are very good for parallel processing and computing large amount of data in short span of time. And these HPC machines, right, the GPU kind of remains to be the core computing engine for most of the AI workloads. Unlike the CPUs that we had in the past, which were very good at supporting and processing a large amount of data, but it were not good enough to support the petabytes of data that is required for running these AI models. And that's where GPU plays a key role, right? Because they are optimized for parallel processing, and also it's making them idle for training deep neural networks. And today's world, if you see, most of the service providers, like whether it be Azure or AWS, all these companies use high-end GPUs like the NVIDIA's A100, H100s, and B100s with high compute and memory and high bandwidth capabilities for these AI workloads. In addition to the GPUs, a lot of the most of these companies have also incorporated the AI accelerators to improve the performance and efficiency, right? For example, if you see, Google Cloud is using the TPUs, which is the tensor processing unit, right? And these are designed for tensor flows and large scale model training. Similarly, AWS is using Trainium and Inferentia, right, which is purpose for built for training and inferencing at scale with much lower cost. And these accelerators have definitely helped to speed up the AI pipeline, not only to reduce the computational side, reduce the power consumption, and but also the hardware cost and also the time for running these models, right? And that is where I think GPU has played a key role. And that's why we said why GPU matters the most in this AI workload is because of the ability to play a dual role in both in training and inferencing an AI model, right? In training, they not only, if you see, speed up the iterative process of adjusting the model weights across large data sets so that they can train fast, effectively, and efficiently. Uh, but also they would be able to get the training done at a quicker amount of time, right? If you see this, NVIDIA's CUDA processors have thousands of, I think, smaller cores that can parallelly process large amount of data very quickly, which is very essential for the training models. Similarly, if you see inference, that enables a real-time prediction for where processing data quickly, and that's where I think these GPU servers play a key role to produce these, I think, inference outputs as fast as possible. And this has that is why GPU has become a very key role. Apart from these servers, right? As we talked about the network and latency aspect in the previous slide, so these service providers have also now invested heavily on these advanced networking technologies like Infinity Band and NVLink, right? Which allows for the faster communication between the GPUs and the nodes. The key thing about these HPC servers is that they are built in a smaller footprint, right? The clusters, the nodes are stayed together. Okay, so they communicate each other because the model runs on a pool of nodes and the nodes constantly talk to each other. So then essentially they require a high networking bandwidth to exchange the information or transfer the data with each other. That's where the technology of infinity band and NV links play a key role for the faster communication. And then comes the memory and storage, right? So high bandwidth memory like the HBM2 and HBM3s have been procured by all these service providers, and also the NVMe storage drives, right, which provides much faster IO operations in today's world when processing this huge amount of data. And the last but not the least is the efficient data centers, right? Eventually, we want effective and fast data centers to be built with the latest technologies, right? Because when we see these GPU servers being built, these GPU servers process a huge amount of data that emit a lot of thermal heat. So companies are investing in liquid immersion and evaporative adiabatic data centers, which are very critical for maintaining a longer life for these GPU nodes, and also powering the data centers, right? Because as we are building these GPU clusters, the GPUs draw a lot of power, right? And it costs company a lot of money. So now the companies like Microsoft are exploring alternate ways to I think to get power to run these data centers, right? For example, they have working on a 3 Mile Island, which had hold a nuclear, I think, power plant, and they are trying to think of generating power through the nuclear sites. So this is one of the cool stuffs that we are currently working on, which is still not in, I think, live, but that's a step in the right direction, I would say. Let's move to the next slide, Emma. Okay, now that we have talked about these GPU offerings, right? So let's talk about the competitors view, right? So various, I think, cloud service provider that I talked about have different cloud offerings today. And if you see, AWS, Azure, or GCP all have, I think, various versions of, I think, VM types. Like AWS has P series, Azure has NCND, and GCP has A series, right? And all these offerings uh, are custom for their own customers and the type of infrastructure they have and the kind of workloads they run on, right? But all offer a similar kind of the GPU models with some, I think, changes, right? Like the NVIDIA V100 is one of the initial versions of the GPUs, which had 8 GPUs, but it had a lower GPU bandwidth, right? If you see, it's 300 gigabits per second with a network capability of 100. It was very good for financial modeling and ML-based training. It was not very advanced. And then we had the next version of GPU offerings, which was the A100s, which was even more advanced, which doubled its GPU bandwidth from the V100s, and it had 4 times more network capability, and which was very good for running this AI training and HPC based training models. Then comes the H100, right, which is the latest versions of the offerings that most of these providers are giving, which has 900 gigabit per second of I think GPU bandwidth and network capability of 400 Gbps, right? And this is extremely good for running the high-end learning models, as well as for inferencing and training and generative AI. And this has been massively adopted by all the AI players. Now, in the future generation, I know companies are working on GB200s, which is the next generation of the GPU servers, which is even more advanced, and people are saying that it's even I think 6 times more. I think capable of computing these of the AI workloads that's being run. So overall, I think all these companies have similar, I think, offerings, but all comes with their own set of, I think, benefits for each of these AI players. So next, I think Emma is going to talk about that. What are the challenges now, Vani?
Sam.
Mhm.
So now that we've discussed the AI workload training requirements that we understand, and we understand the hardware infrastructure that is in place to support them, we can talk about the challenges that arise from the cloud provider's perspective when these AI workloads start running. For example, unfortunately, there are times where hardware will fail on a server. This can be due to various factors like age, corrosion, overheating, despite the cooling that Sam was talking about. However, as we mentioned earlier, the AI training workload is running computations concurrently across many virtual machines hosted on these servers. So if the issue is not prevented in the first place, the training job will be interrupted. Additionally, if that underlying hardware server needs to be repaired, there must be enough capacity to get another server up and running to continue the job. These challenges can start causing delays in a model getting to market. In the next few slides, we will discuss several different challenges that the cloud providers face and how they overcome them. The first theme we will discuss is the availability of computing power. The first challenge is to make sure there's enough GPU capacity in place to support the scale of AI training workloads. There are many macroeconomic factors that have caused constraints on supply amidst growing demand, which then leads to higher prices. Second, these clusters in the cloud have a smaller footprint, and this can potentially lead to scalability challenges when customers go to create or update VMs. Cloud providers need to ensure that customers are not running into creation failures and are able to scale to their needs. Third is that these GPUs are designed to handle these parallel processing tasks efficiently, and hence, as Sam was mentioning, high-speed networking in a dedicated cluster is required to ensure that the training model is performant as possible. Finally, as we mentioned earlier, sometimes these GPU servers need to be sent out of production and into investigation for repair. Since these SKUs are relatively new, the suite of diagnostic tools developed by both the cloud provider and vendor are still undergoing iterations to ensure quick and accurate triage. If there is a particularly challenging debuggability issue, the cloud provider may even need to ship the hardware to the vendor for analysis, and this could take several weeks. Hence, there are many challenges that cloud providers must face to ensure that AI training workloads can run at scale. The second theme that we will talk about is reliability. Training jobs must be up and running to complete model training and get to the market. Interruptions can delay the completion of said model. These types of workload interruptions are different from the typical general purpose issues that cloud providers have been familiar with for years. In fact, Meta published a paper on the new types of failure signatures they saw across their training period for Llama 3 and outlined the many different types of GPU-related issues that they saw from their training model. The other underlying challenge here is to ensure that the cloud provider is capturing all the right telemetry with these new additional hardware pieces and codifying them into deterministic failures, which can then be readable attribution like you see in this chart. Additionally, absolute failures or job interruptions tend to be easier to debug than job slowdowns, and this is a new type of failure scenario that cloud providers have to account for. Another challenge is that the training workloads are extremely sensitive, and updates that may have been impactless to general purpose workloads are now impactful to training workloads. Cloud providers must reestablish their understanding of workload sensitivities to ensure training jobs are uninterrupted. If an impactful update must be made, this requires the training workload to stop running. Every second the workload is down is time lost, and hence updates need to be made quickly across the platform to get the workload back up and running. Lastly, because impactful updates must wait until the training job is no longer running, there could be multiple updates pending that need to be tested together to ensure there are no unintended consequences once the training job starts running, and that could later down the line impact the training job. Hence, there are many considerations that cloud providers need to make to ensure that they prevent reliability issues from occurring in the first place and can quickly root cause and fix them when they do occur. The third theme we will examine is observability. Earlier in this presentation, we talked about training models processing petabytes of data and making trillions of parameter calculations. The sheer volume of data that comes from monitoring this kind of scale is something that cloud providers need to account for and greatly differs from the scale of general purpose workloads. And not only do cloud providers need to be able to collect this data, but they need to be able to identify deterministic issues amidst the noise that can occur across the platform. Additionally, these failures need to be found in near real time and alerted upon. As mentioned earlier, every second the job is down matters, and mitigating the impact by notifying the platform and the customer minimizes job downtime. Letting customers know after the impact occurred is less ideal, and shifting left is necessary to avoid the impact in the first place. If customers are notified before the impact, then they can actually do something about it and move away from the problematic VMs earlier. Finally, it's important to ensure that cloud providers are measuring metrics that matter. For training workloads, new metrics like job uptime must be baselined and actionable for delivering accurate analysis and improvements. Training workloads challenge the traditional way cloud providers have approached logging information, alerting on issues, and tracking improvements. So down to the last theme around responsibility. Last but not least, it is the technologist's responsibility to deliver on safety and ethics despite this go-to-market speed in the industry. First, good data out means that the underlying data going into the model should avoid bias. Bias can be difficult to spot and requires a diverse set of perspectives to ensure a high-quality model is produced. Second, it can be challenging to ensure the AI model details are delivered in an understandable way to stakeholders without a background in AI development. This can cause distrust and concern among stakeholders. Third, there needs to be tight security and audit capabilities for training model development. At the beginning of this presentation, Sam spoke about various applications of AI today. These models hold a lot of power. Finally, it is critical to adhere to regulations for proper data handling. I will now hand it off to Sam to discuss the solutions for overcoming these types of challenges.
Thanks, Emma. I think now that we know that there has been a lot of challenges for these cloud service providers, I think we talked about these four pillars of availability, reliability, observability, and responsibility. Let's look into the solutions, right? These cloud service providers are now getting into, right? The number one is definitely about the debuggability. Then we'll talk about the smart ML predictions, smart scheduling. For reliability, it's all about, again, debuggability will play a role. Again, trying to find interruption, ML-based solutions, shift left with pre-screening hardware, and also testing the environments before deployment, right? And observability will be talking about the anomaly detection, gathering more signals from richer telemetry, I would say, and the customer notifications, right? Responsibility is all about the tools, the governance, the open source technology, and the training technologies that companies are trying to build today. Let's talk about the availability section, right? So I think one of the key things for the cloud service providers is to give availability to the customers, right? At the end of the day, if the AI players, when they come on the cloud, if they don't have the available capacity, then they can't even run the model. Forget about the reliability aspect of it, right? That's even the secondary. Then we should let at least the customers run their, I think, workloads on the cloud. And that's where I think the capacity plays a key role, right? And for this, improved debuggability and diagnostics is very critical, right? Because for these advanced machines, we should be able to repair these servers fast to ensure that recover back as soon as possible, right? So which is very, very critical for driving availability. The second thing is also about the SI dependencies. Considering these are new hardwares, a lot of these cloud service providers don't have a richer, I think, debug muscle within their, I think, in-house, right? And they always have to depend on these SIs like the AMDs or the NVIDIAs of the world to debug if something goes wrong, right? So now a lot of these companies are investing heavily to build that muscle in-house so that they reduce their dependency on the third parties as much as possible so that they can debug issues faster and start, I think, getting these servers back onto the fleet as quickly as possible. The next is we're talking about is the proactive, say, ML-based solutions, right? At the end of the day, a lot of these companies are also now trying to proactively predict the capacity at the region or the DC level, right? It is very important because if you can predict it ahead of the time, then you can take appropriate actions to recover back capacity, right? So that when the customer workloads, its AI workloads scale up, there is enough capacity in that data center or in that region that can support them. And that is where a lot of these companies are building these prediction models. I know within Microsoft, a solution was built, and that was, I think, patented a couple of last year. It was patented of how can we proactively predict capacity at a region and the DC level, and how can we recover back capacity. And next comes the data center spares inventory predictions, right? Because it's very important whenever these machines go for repairs, not only we are able to predict the spare availability, but also we need to ensure that the spares get, I think, replaced as soon as possible, right? If they get into an out of stock scenario, that's a bummer. And I think we don't want that to happen, right? For these expensive machines sitting out for longer time without, I think, generating any revenues for these companies, right? And also impacting the customers. So that is where I think a lot of these companies are investing on ML based spare prediction based on the past historical usage. And the last comes the improved supply and demand forecasting, right? Because if we can forecast better for the demand, and you can look into the existing logistic, I think, supply chain of how the supply is coming through, you can build faster, I think, data centers, right? You need to build out fast to cater to this exploding need of these I think AI infrastructure. So that is where these ML solutions are playing a key role today. The next thing comes for availability is the smart scheduling, right? So we have customers who have extremely critical data to run on these, I think, on these servers on the platform, but also there are some, I think, workloads which are not as critical, right? So it's not mandatory for these cloud service providers to merge or run both the workloads at the same time or in the same region or the hardware, right? So you have to go a little bit smarter there, and that's where I think these companies are working on smart scheduling, where they can schedule the workloads during off peak hours, right? That's again based on the customer discretion, right? If they are okay running certain workloads in the smarter, I think, in an off peak period, they would try to, I think, shift these workloads into an off peak hours. And also they can leverage the ability of running spot VMs, right, which can run for a certain amount of time, shut down, and again reinitiate new set of VMs during a low traffic period, which is going to give a lot more availability for our customers, right? So which is very, very, I think, critical for running the workloads. So these are all the improvements that companies are investing on to drive availability, right? So next comes the reliability, which is the key thing, right? Now we have given them the capacity, we have given them the platform to run the workloads, right? If we are not reliable enough, right, that will lead to a negative customer experience, and which is not at all a good thing for the cloud players. It's a competitive market at the end of the day, right? If one is not doing a good job, the customers are going to go away into other player in the market, right? So that's where reliability plays a key role, and that's where the improved diagnostics again, it is an important pillar here, right, in reliability. The reason is that if you see, if the diagnostic is good enough, then we are not able to find the problems at the right time, right? And we might even have false attributions of the problems, right? If we not take an example, if we have a disk failure, if we tag it as something disk dim or a CPU, then that's not good for the customers, right? It will lead to repeat failure rate, and that is where improved diagnostics and debuggability, I think, is very, very important. That will drive the quality of the fleet. The second thing is the ML based predictions, right? A lot of these companies are investing ML based predictions to predict these hardware failures or platform issues proactively ahead of time, right? Because they have ton of data which they have collected over a period of time, right? So based on the data, they can identify patterns, and I think they can detect these degradations in the platform. They can not only detect but mitigate and remediate these hardware failures, right, or other platform issues, which is very, very good, right? Because even before your customer sees or even the customer gets impacted, the cloud service providers platform is proactively identifying these issues and then migrating the workloads, right, to ensure that the customer experience doesn't go down or the AI models doesn't get impacted. And it is a very key thing, because if you see the ML models, once they get impacted, it takes a more amount of time for them to come back up and running, right? The efficiency of the model gets lost quite a bit. So that is where these AI players don't like their work models getting hit quite a lot, and that's where this ML based prediction model plays a key role in proactively identifying these, I think, platform issues. Then comes the shift left initiatives, right? I think before even the customer workloads land on these hardwares, right, it's very, very important to screen your fleet, right? This hardware should get screened beforehand. If there is a defective component within the servers, or if there is some additional, I think, capabilities that these servers cannot handle, so we try to replicate, and these companies do a lot of stress testing on these hardwares in the build out section, or even releasing the servers infrastructure out to the production, right? They do a lot of testing, stress testing, to catch the issues before time, right? And if there is any latency issues or if there's performance issues. So all these things have played a key role actually to building a healthier fleet. And last comes the deployment strategies, right? Because as if you see, ML workloads can dial up any point of time, also they dial down, right, based on the kind of data they are feeding into the model. So it is very very important that we have actually good deployment strategies in place, right? Why it is critical? Because when the deployments that cloud service providers have to do on these machines to support the customers, they shouldn't break their models actually, right? That they shouldn't interrupt them. And that is where companies are trying to replicate this customer's environment, like building synthetic workloads where they can test their updates, and if something is breaking, better they fix it before putting it onto their real customer, I think, machines having the workloads. And also the last is the control and planned maintenance, right? Because sometimes if you see, when the cloud service providers are deploying the loads, it's very important for them to plan it, right? They can notify the customers that we are doing something, we are deploying a fix, or we are deploying certain firmwares, or operating system is new patch of operating system is getting deployed. So better this customer is aware that they have to do something, right? Sometimes we go on the empty servers first, but if there are VMs or the customer load is running, then these AI players, like the cloud service providers, try to work with the AI players in tandem to ensure that they are informed, and whatever coordinated deployment can be done, they are doing it nowadays, which is better. So now let's quickly move into the reliability section, the observability section, right? So as we are talking about, right, AI models requires to run on these complex machines, but we have ton and ton of data that's get, I think, generated through all these things, right? We have telemetry at the hardware level, at the platform level, or at an operational level, right? When these models run, right? So what do we do with this data, right? So that's where I think all these, I think, companies, I know in Microsoft we are heavily investing on AI ops, where we look at the data, we identify patterns, right? We again run ML based algorithms to find, uh, I think, bugs to keep the other ML algorithms or AI algorithms to run, right? So that is, I think, a unique thing, right? So we look at these richer telemetry that we have collected over time, right? And then we identify these runtime anomalies within the system, right? Based on the patterns that we identify. And then we are triggering the cloud-based alarms or these incident tickets for the teams who see these anomalies and fix them ahead of time, so that the ML workloads doesn't get impacted. The second thing is the observability is the telemetry part of these machines itself, right? Because these are newer machines with newer hardware, and if you see, GPU is a new, I think, kind of, I think, architecture, right? So it is very important to understand that what kind of in in system telemetry we can generate out of these, I think, machines, right? So that's where companies are investing hard to get the in hardware telemetry, so that they can look for these, I think, degradation signals from these GPUs, which can help identify when a GPU goes bad. It can lead to a slowness of these ML workloads, right, which can lead to reductions or job crashes. So that is another investment that is that's being done by these companies for observability aspect. The last is the customer notification, right? If you see, once we've identified all these, I think, issues in the platform, right, whether it be reliability issue or observability, through, I think, ML based prediction, right? But what if we don't notify our customers, right? That's where the trust is get built for our business, right? And so these companies are trying to build a real time notification system, which a lot of the companies already have, but they are spending more and more to give more near real time signals to the customers, that if something in the platform is degrading, then they better, I think, evict their workloads and move to a healthier hardware, right? And it's a more coordinated effort. I think all these service providers are trying to achieve that, and it is very very critical to to ensure that their workloads doesn't get impacted. And that's where I think customer notifications are playing a key role nowadays. Last, I think, pillar is the responsibility, right? I think, as we have been dealing with ton of data, I think all the players have to be, I think, responsible enough, right, when dealing with this critical sensitive information. That's where the pillars of AI principles and governance have been built. I think defining AI standards is one of the key things for driving responsibility. I know Microsoft is championing in that as of today. I know Ether Committee and Office of Responsible AI is one of the key, I think, investments we have done to follow, define the principles and define a governance plan around it, right? And also, I believe a lot of the companies are building bias mitigation tools, right? Like Azure has this fairness toolkit, Google has is doing AI fairness indicators, And also we have SageMaker Clarify to identify and reduce the algorithm bias. And also we have stricter, I think, data protection policies, right? As we deal with a lot of data, so I think we shouldn't allow the customer data to get trained in the model, right? So it is very, very important that we don't breach that trust with our end users or the customers. And also we have to adhere to the compliance that Emma was talking about previously, about the GDPR, CCPA, and there are others as well based on different countries. Apart from these, I think the training plays a key role. You have to have training programs, you have to have certifications, you need to build documentations, keep training your people so that they don't miss out how important responsibility is in the world of AI. And last is building the open source technology, right, and public facing documentation. At the end of the day, the tribal, I think we don't want information to be tribal, right? The knowledge, if it's in-house, then only some people can use it, right? At the end of the day, we want it to be as global as possible. It should be get a broader reach. That's why I think these public facing documentations and open source technology is going to build a responsible, I think, society for running these AI workloads overall. Next, I'll give it to Emma for running the last slide for conclusion.
Thanks, Sam. We covered a lot of ground today. So in conclusion, AI models will become only more complex and require more computing power, and hence cloud infrastructure must rise to meet those needs. We do know that the ethics and safety piece will be something that's ongoing and is a responsibility of all technologists, and should remain a priority even with these space races going on. So we are thankful that you have helped stick around for the presentation, and we are excited to get some questions going. Thank you.
Excellent. What a great presentation. So timely, so interesting. We have one question in the chat, and Gustavo, I'll let you ask that. Gustavo, are you there?
Yes, thank you,
Okay.
Chris.
Yeah, you're welcome.
Well, last year, IEEE Spectrum published an article on the company called Sagens that was working on analog neural networks to reduce the power needs of the AI applications. I don't know if you can have any comment or if that company disappeared or what happened with them.
I personally am not aware of what the storyline was around that. I'm interested, so we'll look into it. Sam, I don't want to speak for you though.
No, I think I haven't heard about it either, I think, honestly.
Neither I. So it was surprising for me to hear about analog, but they say they reduce 10% the amount of power needed for Llama 2 application. So strange. Let's investigate. Thank you.
Yeah,
Interesting.
thanks a lot.
Thank you.
I had a question. So the our deal with OpenAI. So does OpenAI? Do you know what percentage, or like, is most of the load or a majority of the load on our servers, on our AI servers, from OpenAI, or is it from everywhere? Or do you know? You might not know, or you might not be able to tell us.
Yeah, I don't know if we're able to disclose the exact percentage. I can at least confirm there's definitely a good amount of OpenAI workloads running on the servers that Sam was talking about that are packaged specifically for HPC workloads. But Sam, I don't know if you want to chime in there as well.
No, I think we have OpenAI. We have other customers too, I think, whom we are onboarding, and we have onboarded already. I cannot disclose the names, but definitely OpenAI is a big player for us. On top of that, Microsoft in-house Copilot also consumes a lot of the server capacity that we have, right? So we are also building in-house, right? So that's another, I think, piece of the pie where I think.
Right. I work on the DAX Copilot, and we're definitely using a lot. I know that. So let's see. Is there any other questions? Okay, everybody's saying they love the presentation. I still have more. I can definitely ask more questions. So what's really interesting to me about this, it seems like a lot of the work you're describing is just in the last year. Is it been going on for years, this buildup? Because not too long ago, maybe a year or two ago, wasn't Microsoft like running out of power? You know, like we were low on hardware. Remember the shortage of chips? And now it seems like we're ramping up again. Is that what I'm seeing?
That's correct.
Take that one, Sam. Yeah.
Yeah, I think, yes, I think in around 2020, 2021, with the COVID hitting and supply chain challenges, I think not only for AI, right? I think across the fleet, I think we hit a lot of challenges, Christine, there. But for AI and for other kind of, I think, workloads, we felt the heat quite a lot more. Because if you see the nature of the fleet for these machines are like they are smaller footprint, as Emma pointed out, right? These are expensive machines. We don't invest a lot of money in building how we do for this general purpose machines, which are way cheaper, and they are at scale, right? They are in millions in count for us, right? And when it compares to GPC servers or the other set of, I think, SAP based machines, there's a lot of companies own, they are smaller footprint. And when they are smaller footprint, if suddenly the demand increases, right, it's very difficult to scale up. And that's where we saw some challenges. And that's where the solutions that I talked about, right, the ML based prediction and demand and forecasting, and ML-based solutions for, I think, recovering Mac nodes sooner when they are unavailable for customers are all what investments we did during those crunch situations, which are very fascinating.
And that's all done in software, right?
Yes.
Yes. Software's king. I love it. Yeah. So I'm just looking at an article right now. This is from The Information. The title of it is OpenAI leaders say, and this was from October of 24, so over a year ago, right? And it's saying OpenAI leaders say Microsoft isn't moving fast enough to supply servers. And they were discussing a deal with Oracle to build the world's most powerful AI data center, but Microsoft promised OpenAI 300 NVIDIA GB200 chips by the end of 2025. So it looks like we're racing really hard. I mean, it's like you said, it's not just OpenAI, right? It's all our customers are doing this. And I think it's just been, your team probably has really had to fight hard to meet this demand and make sure it can be met, right?
Exactly, right. And if you see today, we are investing on GB200s. I think that's what I called about it. That's next gen of high-end machines, which is, I think, after H100 machines, right? And we are already, I think, started doing that, right? So it has, I think, to an extent, I don't know if it's open to public or not, I think, for the AI players, but I know for sure that a lot of testing is happening. And definitely, I think we are there. So the key important message we want to give is the faster we build out, I think the better is for us, right? I think building out these machines from scratch takes a lot of time because the complexity of the hardware is like that, right? It's not like any other machine. So that's where I think Microsoft is heavily investing on to bring efficiency in building out these machines, not at a data center level, right? Not only from logistic perspective, but also I think starting from procuring from SI versus when it's live and running. So that entire cycle is getting shortened more and more for these AI machines. To keep up with the demand for these AI customers.
And just to add on to that too, there is
go ahead.
The hardware component of this, of like securing the machines, like you were mentioning, Christine and Sam, but there's also, making sure all the internal routing and all that kind of good stuff, like the telemetry, the attribution is also coming together. So it's not just a race to secure the hardware, but it's also a race to make sure all the internal plumbing and, debuggability in those pieces are also set up. So it's kind of it's a team-wide effort across hardware and software for sure.
Wow. Yeah, I know that for sure, for the work we do. So it is at that time. There's no more questions. I want to thank you both. This was so interesting, and I can't wait to see you at the IEEE conference on AI. And I think we'll talk about, I think you should do this presentation again or something like it, because this was so good. But thank you so much. Actually, Gustavo, if you want to grab it, he just put the Sagents link in the chat if you want to grab it and take a look.
Sure.
While you have it, yeah, because I know sometimes when Zoom goes away, we lose it. Thanks again so much to Sam and Emma. Thanks to the participants and Chris Franzino for doing all the tech work here. And have a great weekend, everyone.
Thank you
Thanks.
all.
Thanks, everyone.
Thank you.
Great weekend.
Thanks a lot. Take care. Bye-bye.